6, and here we're going to be looking at the sampling distribution and the central limit theorem, and then in the very end assessing. So the first thing we need to do is sampling distribution of sample means. It is a probability distribution of sample means, so we're going to have a bunch of samples. We're going to take the mean of each of these samples, and these sample means will be our values for our samples. For example, suppose we have a population consisting of 3 data points, 1, 4, and 7. The mean of this is 1 plus 4 plus 7 divided by 3 is 4. The standard deviation, if you use the formula for standard deviation, you would get that it is about 2.45. And now we're going to consider all possible samples with replacement of size 2. So all the possible samples. We could have a 1 and a 1. And the mean of 1 plus 1 divided by 2 is 1. We could have a 1 and a 4, and 1 plus 4 divided by 2 is 2.5. We could have a 1 and a 7, which the 1 plus 7 divided by 2 is 4. 4 and 1, 4 and 4, 4 and 7, 7 and 1, 7 and 4, 7 and 7. If we add up, now note we have 9 possible samples here, and 9 possible sample means. 9. And we get 4. And the standard deviation in this case is, we do the long formula. Yeah, I'm not expecting you to be able to do that. I'm just telling you I did it, and it's about the square root of 3. This is approximately equal to the original standard deviation of 2.45 divided by the square root of the sample size of 2. This is important. So the value of a statistic, such as a sample mean, depends on particular values included in the sample, and it varies from sample to sample. This variability is called sampling variability. We can also look at sampling distributions of the proportion. I'm going to kind of go through this quickly because these are not problems that I need you to understand what this sampling distribution does, because we're going to be using it in a much more important part, which is the next section. We can do the proportions, but this time we still have our 1, 4, and 7, and we're going to look at numbers. Between the 1 and the 4, one of those, the 4 is an even number. 1 out of 2 is even. 0, 1, and 7, neither is even, so forth, okay? Now we add those numbers up to and we get 3/9, 3 out of 9, or 1/3. Okay, so the properties of the distribution of the sample proportions are: sample proportions tend to target the value of the population proportion, and sample proportions sometimes approximate a normal distribution. Samples that target population parameters are the mean, the variance, and proportion. What estimates the parameters poorly? Some sample statistics do not estimate population parameters well, and they're called biased estimators. Standard deviation is a biased estimator, so is the median, and so is the range. But standard deviation does not target the population standard deviation well, but if the bias is relatively small in large samples, so it's often used to estimate the population standard deviation in larger samples. Just needed you to get the big picture. And I know some of you got the big picture is very cloudy, but this is the more important part, the central limit theorem. The central limit theorem says, suppose we have a variable that may or may not be normally distributed, and it has a mean and a standard deviation. Then when we take simple random samples, all of the same size n, and each sample has the same chance of being selected, so it's randomly selected. Then, conclusions. The distribution of sample means will, as the sample size increases, approach the normal distribution. The mean of all the sample means will always be equal to the true population mean, and the standard deviation of all the sample means is the population standard deviation divided by the square root of the sample size. That's what we saw when we looked at the first example in 6.3 on the sampling distribution of sample means with our example of the 1, the 4, and the 7. population is not normally distributed, but the sample size is greater than 30, then it will be approximately normally distributed, and that approximation gets better as n gets larger. We're going to use this fact that if n is greater than 30, that it'll be approximately normally distributed. We're going to use that in chapter 7. But if the original population was normally distributed, then the sample means of any size sample will be normally distributed. So which would have less variation from the population mean, a single value or the sample mean? Sample mean would, of course, because a single value, if we think of the height of women, there's very short women, there's very tall women, there's average. But if I took a sample of 20 women, the very tall and the very short would kind of average each other out. So a sample mean has less variation from the true population average height of a woman. The notation for sampling distributions of sample means. We have the mu sub x bar, which means the mean of the sample means. And remember, we just said a few slides ago, that's equal to the population mean mu. And sigma of x bar is equal to the population standard deviation divided by the square root of the sample size. That term is called the standard error of the mean. And we're going to use that again in chapter 7. The rest of the stuff was just ideas that you needed to understand to get this. So when we did z equal to value minus mean divided by standard deviation. But if we're doing for z for a sample mean, it's this sample mean minus the mu of x bar over the sigma of x bar, which remember is mu of x bar is equal to mu, and sigma of x bar is equal to the sigma divided by the square root of n. You're going to have to do this calculation even using Minitab. And I'm going to show you an example in just a minute. So using Minitab, you're going to calculate that new standard deviation, the one that we call the standard error of the mean, and then do the procedure just as we did before in 6.2. So for example, suppose we have one man who's randomly selected. We want to find out the probability that his weight is less than 167. We go to Calc, Probability Distributions Normal, select Cumulative Probability. We enter in the mean of 172 and the standard deviation of 29 because we're looking for just one man. This is what we were doing earlier when we were in 6.2. Then the answer is 0.4316. That's the probability that one man has a weight less than 167. Let's continue with this example now and find the probability of the 36 men, the average of their weight, the average of the 36 men being less than 167. This time, remember, the mean of the x bar is the same thing as the population mean, so it's still 172. But the standard deviation for sample means is the population standard deviation of 29 divided by the square root of 36, which is 4.83. So you enter in the standard deviation being 4.83. The input constant is still 167. If you do these two parts of this problem back to back, the only thing you've changed from part A with the one man to part B with the 36 men is you change the standard deviation from 29 to 4.83. And look, it did change the answer. It changed it to 0.1503. All right, now, sometimes we have to assess normality, and we can do that with Minitab. Or we can actually draw a histogram, and if the histogram differs dramatically from a bell shape, then it's not normally distributed. And if it sort of looks like a bell shape, then we'd say it's approximately normally distributed. We can look for outliers. If we have too many outliers, we reject normality. Or we can also do a normal probability plot. Minitab will do this normal probability plot for us. We're not going to do this by hand. This is if you were doing it by hand. And your book does cover an example of how to do it by hand, but we're just going to let Minitab do it for us. But it's the value, and the y values are the z-scores that correspond to that. But we often do this through technology, and we're going to use Minitab. So let's see. We're going to look to see how to do it by hand to better understand what it is, but we're going to go very quickly because there's not one of you who are going to want to do it by hand. All right, so you sort the data from lowest to highest, then you calculate each of these values, 1 over 2n, 3 over 2n, 5 over 2n, and so forth. Then you use the standard normal table to find these z-scores, and so forth. You match these z-scores with the values, and if you graph these points, if they lie close to a straight line, then it's not normal. If they do not lie close to a straight line, they are not normal. If they do look fairly linear, they are normally distributed. Now what Minitab is going to do is do all that for you. It's going to graph it. It's going to show you those dots on a line. And you're going to see, do they look like they're following randomly on either side of the line? Does it have a kind of a linear look to it or not? And the more points you have, the more strictly they must seem linear. Plot. So let's look at the example in the data set, the Minitab data set. I have this either on the portal under Minitab datasets called irises, or you can find them at www.triolastat.com, and you can download all these datasets yourself and download them as Minitab datasets. So you open the dataset iris and you use the column PL for petal length. You go to graph, probability plot simple, enter in the column PL, and then hit OK. Now notice when we do that, the points do not follow the line. And look in the bottom right corner of that graph, and it has something called a p-value, and it says it's less than 0.005. Whenever this p-value is less than 0.05, we say the data is not normally distributed. So you take a look at the pictures, the points do not look like they're following the line. Also, that p-value is less than 0.05, so we would say that the petal length of these irises does not follow a normal distribution. Of your assignments on the MyMathLab website. All of Chapter 6 is a unit in itself. It's that important, so that's why I put it all by itself in its own unit. You can watch the lecture recording for Lab 6. You download Lab 6, complete the lab, type in your answers and save as a Word document, or handwrite in your answers and scan and save as a PDF. Please do not attempt to take pictures of these labs and think that I can grade a picture, because I can't see it well enough to grade. Then you upload it to the portal. If you have any questions on either the homework assignments or the labs or any of this lecture, please do not hesitate to contact me. Thank you.